Hello and welcome back to Pyman Tutoring. Today we're going to be looking at graphing functions now that we understand how to do the first and second derivatives of functions. Let's begin. Suppose you are given the function f of x is equal to x plus 1 divided by x squared minus x minus 2. Now, before we learned about derivatives, we would have tried to plot this graph by looking for some specific features of the function. So, for example, we would maybe first try to factor the denominator and see if we've got any holes in the function. So let's do that first. We're looking for two factors that have a product of minus 2 and a sum of minus 1. So that would be a negative 2 and a positive 1. So we've managed to factor the denominator, and we've got a common factor in the numerator and the denominator, so we can cancel those out and reduce this function down to simply 1 over x minus 2, and with a hole in the function at x equals negative 1. So after looking for holes, we could also look for vertical asymptotes. Well, in this case we know that when x equals 2, the denominator becomes 0, and so we have a vertical asymptote at x equals 2. We look for horizontal asymptotes, and in this case, as x tends to infinity, we can see that f of x tends to 0. So we have a horizontal asymptote at y equals 0. And as x heads in the other direction to minus infinity, we end up with 1 divided by minus infinity. So again we are approaching a value of 0, but from the other side of the axis. So that's all fairly straightforward. We normally also look for the intercepts. So what happens when x equals 0, or the y-axis intercept, and when y equals 0, which is the x-axis intercept. And all of these features have helped us to be able to plot functions like this without the aid of any calculus. So let's just quickly look at what this one looks like. We said we've got a vertical asymptote at 2. Let's assume this is x equals 2. We know that the function is approaching 0 as x tends to infinity. And the thing to do is to look at the behavior just to the right and to the left of that asymptote. So if x is a little bit bigger than 2, then the function 1 over x minus 2 would be 1 divided by a very small positive number. So we must be approaching infinity in this direction when we are just above the value of 2. And we know we have a horizontal asymptote at 0. And similarly, if we were slightly to the left of 2, so 1.99, then the function 1 over x minus 2 would be a very large negative number. So we know the function has this kind of direction, and again it is approaching 0 as x tends to infinity. We don't have any x-intercepts in this case. We could solve for this y-intercept. So let's quickly do that. we will simply feed in that x is equal to 0, and so f of x would be 1 divided by x minus 2, which is 1 divided by negative 2, or negative 0.5. So this is the point 0, negative 0.5. So that approach works pretty well for reasonably simple functions like this, and we don't need any other tools. But if we have some more complicated functions, we can start to use the derivative, both the first derivative and the second derivative, to give us additional information. So let's take a look at that. So let's first remind ourselves what we mean by the derivative. So we have some f of x, and then we're going to calculate f dashed of x. And the f dashed gives us the slope of the tangent to the function f of x at any given value of x we choose. And so this is the slope of the tangent at x. And so if this has a positive value, then we know the function is going up to the right, which means the function is increasing. And similarly, if the value of the tangent is negative, then we know the slope is negative, and therefore the value of the function is decreasing. It's decreasing because the values of f of x are getting smaller as x increases. So x is going up and f of x is going down. When it's increasing, as x goes up, f of x is also going up. So we can use the derivative function to give us information about where the function is sloping up to the right or down to the right. And this can be important in finding what we call local extrema. Now, the term local extrema simply means that the function achieves some extreme value at some point locally within the function. Let's look at what we mean by that. So here's a couple of rough sketches. Suppose we have a function that looks something like, let's say it looks like this. And another function that looks something like this. So just to clarify what we mean by local extrema, as we scan through we'll call this the domain of this function, let's say it's only defined over this range, then we can see that in this location we have a peak, and in this location we have a valley, and in this location we have a peak. So locally there is a maximum value here, a local maximum. And the same here, there's a local maximum. If we choose this singular point and we look to the left or right, the value of f of x is smaller on either side of this point. And similarly here at the very peak, doesn't matter which way I look, if I look to larger values of x or smaller values of x, the value of f of x is going down, so I'm at the peak. And here, down in this little valley here, I have a local minimum. And that means that if I look to bigger values of x, f of x is getting bigger, and if I look to smaller values of x, f of x is getting bigger. And therefore I'm in a valley, I'm at a local minimum. Down here we have the lowest value of the function. So this is not what we would call a local minimum, this is what we would call the absolute minimum within the domain that's defined. And it just so happens that this local maximum over here is also the absolute maximum of this function. If we go to the second function, similar idea. Let's just continue that graph to here. Again, we will say that this is the entire domain of this function, and then we can label various points. So here we have a local bump, and so that is a local max. We have two valleys here and here, so those are both local minima. We have an absolute max value here, the highest value within the domain, and the lowest value within the domain is the two local minima. It's not too clear what's going on here. It looks like we've reached a local maximum, but we don't know what's happening on the other side. This function is not defined to the left, so this is a little bit of an ambiguous case. We could call this a local max, since there is no x value to the left of it. We can only go to the right, and if we go to the right, f of x is decreasing, so we could classify that as a local maximum. Okay, so that's just a clarification on what we mean by some of the terminology. Now let's look at some of the basic shapes that we can expect when we are drawing curves. So let's start with four basic shapes. If a function is increasing, it could have this kind of shape, or it could have this kind of shape. In both cases, as x is increasing, our value of f of x is increasing. What's different is that in case number 1, we'll call this 1, the steepness of the curve is reducing. So we are increasing but at a decreasing rate. In case number 2, the slope is again positive. Let's just draw the slope on here. So here is the initial slope, here is the slope sometime later, here is the slope sometime later. So they're all positive, so the function is increasing, but it's increasing at a decreasing rate because the slopes are getting less steep. In contrast, this second function is getting steeper and steeper and steeper. In both cases, f dashed of x is positive. F dashed of x, positive. The slope is positive, so the derivative is positive. Now, let's look at the two other cases. So we could have a decreasing function. We could look like this. We'll call that number 3. And we can also have a decreasing function that's shaped in the other direction. We'll call that 4. So let's again just look at the slope of each of these. So here the slope is negative, it's still negative, it's still negative, but it's getting shallower and shallower. So here f dashed of x has a negative value. Over here, in example number 4, we have negative slopes, but look, they're getting steeper and steeper and steeper. So we can say f dashed of x is also negative, but it's getting more negative. Getting more negative. And getting less negative. So those 4 types of curvature are obviously typical of what we might see when we plot a function. And what happens when we get a couple of those close together? So if we have 1 adjacent to 4, we're going to have a function that is positive but tending towards a slope of 0, followed by a part of the function that is negative and getting more and more negative. And if we have that case, I think you can probably see that at the top here, the tangent to the graph will be 0. So f dashed of x will be 0 as we transition from type 1 to type 4. And because we are going from f dashed of x positive to f dashed of x negative, we create a maximum, a local maximum. And this is what we refer to as the first derivative test. It means that if you can find values of x such that the gradient, the slope, the derivative is 0, and then you look at what the derivative is doing on either side of that 0, you can determine whether you have a maximum or a minimum. And we call that the first derivative test. Now similarly, if we combine an area of the graph with shape 3, and it is adjacent to an area of the graph with shape 2, we're going to get something that looks like this, followed by something that looks like this. And once again, at the point where the slope changes from negative to positive, we're going to pass through a point where the slope is actually instantaneously 0. So again, f dashed of x here will be 0, and in order to find out whether that is a maximum or a minimum point, we evaluate f dashed of x on either side of that particular point, and if we find that it is negative to the left and positive to the right, then that means we must have a minimum at that point. And again, this is the first derivative test. Depending on how the sign changes, if it goes from positive to negative, it's a maximum, and if it goes negative to positive, it's a minimum. Now you could have a third type. You could have 1 combined with, let's say, 2. So we're going to have a shape like this for 1, and then it's going to turn into a shape like this for 2. Now again, when you do the derivative of the function and you look for zeros, you'll pick one up at this point where the graph changes direction. So f dashed of x will be 0, and if you look for what happens to the derivative, the sign of the derivative as you pass through that point, in this particular case, what are you going to see? You're going to see a positive value before you hit that critical point, and you're going to see positive again when you come out the other side. So you've got positive going to positive, and we call this an inflection point. And similarly, you could do the same thing with other shapes. You could be coming this way and going this way, or what else could you do? You could go this way followed by this way. So depending on what curvatures combine, there are various ways in which you can produce inflection points in the curve. Now again, in terms of terminology, we introduce the concept of critical points. And what we've been doing below here is finding f dashed of x equal to 0. And if that occurs at a value of c, so let's just erase that for a second and call this actually a c. If you find points where the derivative is 0, you know you're looking at some change in the slope at that point, the sign of the slope, or possibly an inflection point. So with further investigation, using the first derivative test, you can determine what is the nature of the critical point that you have found. Now it's also possible that you might find some points where the first derivative does not exist, and these are also critical points. If for some reason the slope goes off to infinity or minus infinity, in some way is not defined, then there's also something interesting going on with the curve at that point and needs further investigation. So one of the first things we do when we are going to the next step of plotting graphs is to find the critical points. So let's look at some other basic shapes that you will encounter in plotting graphs. One is a cusp, and this is where we have some positive curvature immediately followed by some negative curvature. And so this point here where the curve abruptly changes is a critical point. If you try to find the derivative of such a function at that point, you would find that it does not exist. The function is not differentiable at a cusp. But as you can see, this actually represents a local maximum, because we have got positive on one side of the critical point and a negative slope on the other side. Positive going to negative is max. And of course cusps can go also in the other direction. So we could have function going this way and then immediately turning and going this way. Again, this is a critical point, and in this case we have a local minimum. And as we can see, we have a negative slope instantaneously turning into a positive slope. Very similar to the cusp is the corner. So, except here we're dealing with linear things. So if a function is linear up to some critical point and then abruptly changes direction in this fashion, there's a discontinuity in the function at that point. And again, we would find that the function is not differentiable. But as you can see, it's possible to have a local max in such cases, just like a cusp or a local minimum. And the final feature, and we've already talked about this a little bit, just to remind you that it is possible that we will have vertical asymptotes at some point in the functions we're investigating. So something like this, for example. And again, this is a critical point. If you try to do the derivative of this function at that point, you would find that it does not exist. It's not a maximum, it's not a minimum. Notice in this case we have an increasingly positive slope on one side of the critical point, and on the other side again it's positive. So we have positive going to positive. We could have negative going to negative slope, and we could have positive going to negative and negative going to positive, right? Because we could each equally have an asymptote that does something like this. Now we should introduce one other key concept before we move on. Remember, we drew this diagram that showed a function that is increasing, so f dashed of x positive. We said that there is another version of curvature where f dashed of x is also positive. And then we had the two negative cases, so one that is getting more negative and one that is getting less negative. So here we introduce the concept of the second derivative. The first derivative gives you the rate of change of the function itself. So we have the function, we produce the derivative, and that is equal to the rate of change of the function. And what happens if we do a derivative again, and we call that f double dashed of x? Using our same derivative rules, we're now going to get a rate of change again, but this time it's the rate of change of f dashed of x. So it tells us how the slope is changing. So over here in type 1, the slope is positive, but it's getting less positive, and therefore the second derivative of x in this quadrant would be negative. The rate of change of the slope is negative. We've got positive values becoming less positive. Less positive means negative. Down here in the bottom right quadrant, things are getting steeper. So if we took the second derivative down here, we would find that it is positive. Here's the slope at one value of x, the next value of x, it is bigger. And so the slope is increasing positive. What about the negative case? So down here in the left-hand corner we have a negative slope, but it's becoming less negative. Less negative means positive. And so our second derivative down in this quadrant would be positive. And finally, in the top right-hand corner, we've got a negative slope, and it's becoming more negative. And so my second derivative, my rate of change of the slope, is negative because I'm getting more negative. So what this means is we can use the second derivative at critical points to help us determine what is going on. So let's suppose for a moment that you have found some value of c, some critical value, where the derivative of the function is equal to 0. And you're trying to find out whether it's a minimum, maximum, or inflection point. So you can do the first derivative test. Let's suppose this is our function. So you have found some value of c here where the slope is 0. And you could evaluate the first derivative on the left side, the first derivative on the right side, and you would conclude using the first derivative test that this is a minimum. And that's because f dashed of x is going from a negative value to a positive value. Another way you could do this is by using the second derivative, because the second derivative gives us the rate of change of the first derivative. But at a minimum, my rate of change of f dashed of x, since I'm going from a negative value to a positive value, it must be positive. But the rate of change of f dashed is simply f double dashed of x. And so we can say at this critical point here, c, f double dashed of c must be greater than 0 for a minimum. And of course the opposite is true, that if this function was curved in the other direction, then we know that f dashed of x is going from positive value to a negative value, and that means that the rate of change of f dashed must be negative. So f double dashed of c in this case must be less than 0. And we call this the concavity. This downward facing shape is concave down, the upward facing shape is concave up. So if you do the second derivative and find it's positive, that means you've got concave up. And if you do the second derivative and get a negative value, that tells you you're concave down. If you do the second derivative and you get a 0, then things are a little more ambiguous. F double dashed of c comes out to be 0. What does that mean? Well, if it's not a maximum and it's not a minimum, one thing it can be is our friend the inflection point. but it's only an inflection point if the concavity is changing at that point. So here we have concave down for this function, and here we have concave up. So it's an inflection point if the sign of f double dashed of x changes at c. So it is possible to get a second derivative that is 0 and it's not an inflection point. So be careful with that. F double dash equals 0 does not guarantee that it is an inflection point. You must do the second derivative test. The second derivative test is to check the concavity or the sign of the second derivative on either side of the critical point. So let's just write that up here. Check for sign change in f double dashed of x at critical point. So we pretty much have all the tools we need to be able to plot any function that's thrown at us. The only other thing we need is a simple way of tabulating critical points and the behavior of the function at those critical points. So a strip is just a way of showing the critical points that we've determined and the behavior of the function and its derivatives around those critical points. So let's say we've been given some function f of x, and we've done the derivative f dashed of x, we've set it equal to 0, and we have found critical points. Also where the derivative does not exist, remember. So we have found some critical points, let's call them C1 and C2 and C3. Once we have those critical points, we place them on a number line, a C1, C2 and C3, and typically we create 3 strips, and each of those strips will be used to indicate the behavior of f of x, f dashed of x, and potentially f double dashed of x if we need it, in order to see what the function is doing. Let's look at a quick example to make this a little easier to understand. Let's suppose we have f of x is x to the 4 minus 8x cubed plus 18x squared. Now clearly that can be factored. We can pull out an x squared from that. So let's do that. X squared minus 8x plus 18. And that might help us to find zeros of the function itself. So clearly when x is 0, the function is 0. And so we can mark that. Let's suppose our C2 value is 0, right there. And what we're saying is the function has a 0 at that location. X equals 0. And since it's x squared, it is actually a double 0. So we would usually put 2 lines there to indicate a double 0. And if we do look at the discriminant on the other part of this expression to see whether we have any other roots from this second part, b squared minus 4ac, so b squared would be 64 minus 4 lots of a is 1, C is 18. So that's 64 minus 72. That's negative. So we're going to be trying to find the square root of a negative number, and therefore we don't have any other zeros in this case. Now we look at the derivative function of x, f dashed of x, using the power rule. So we bring down the 4, makes that x cubed. Bring down the 3, makes 24x squared. Bring down the 2, makes 36x. And now we can pull out a common factor of 4x from this, leaving us with x squared minus 4 6s are 24, and plus 9. And if we continue factoring, we'll get 4x into x minus 3 squared. Okay, so for this to be 0, we need x to be 0, or x is equal to 3, 3 being a double root. So let's say we have C3 is a 3 over here. Then we know that we have 1 0 for the derivative at 0, and we have a double 0 at x equals 3. So we only have 2 critical points. We don't have a C1, so we'll dispense with the C1. Now we can start to feed in the behavior in the strips. So for f dashed of x, we know that we can choose any value to the left of 0, any value on this side. So let's choose a -1, and if we feed that into f dashed of x, we'll get -4 multiplied by something squared. Well, something squared is always positive, and so the 4x term is always going to give me negative in this part of the domain. If I'm between 0 and 3, so let's choose x equals 1, then I'm going to get 4 lots of 1, so that's 4, and again a squared number is always going to be positive, so this is always going to be positive. And if I'm at a number greater than 3, clearly 4 times 4 is 16, the squared is positive, so it remains positive out here. So what can we see just from the first derivative? We can see we've got a negative derivative, so the function is going down here, and when it gets to 0 it becomes positive. So those are the conditions for a minimum. When I get to C3, or the value of 3, I've got a positive slope, and it's positive on the other side as well. And briefly, it's at 0, so it looks like I'm going positive slope and then positive slope again. It looks like we have a possible inflection point. Now if we want to guarantee that, we can do the second derivative test, and for that we need to work out the second derivative. So let's do that. Let's go up into this space up here. So the second derivative of x, well, we need to do the derivative of this product down here. We know how to do the derivative of products. We do the first function times the derivative of the second. So we'll bring down the 2, x minus 3, reduce the power to a 1, multiply by the derivative of the bracket, which is just a 1. And then we have to add the derivative of the first function, which is just the 4, multiplied by the second function. Well, clearly we have a common factor of x minus 3, so let's pull that out. and we're left with 8x plus 4 lots of x minus 3. That's x minus 3 into 12x minus 12, or pulling out a factor of 12, 12 into x minus 3, x minus 1. So the second derivative has zeros at x equals 3 and x equals 1. Let's put those in the chart. Zeros at x equals 3 and also a 0 at x equals 1. So it could be that we have two inflection points in this particular curve. Let's see what we've got. Let's look at the value or the sign of f double dashed of x in these various zones. So remember, this is a value of 1 here. So if x is less than 1, then this term will be negative, and this term will be negative, and so in here we're going to be positive. So that tells me if I've got a positive second derivative, my shape is going this way up to a value of 1, and that's consistent with these two slopes down here. Now what happens when I get to 1? Well, let's choose a test value of 2 for the f double dashed. If I put a 2 in here, I'll get 2 minus 3, so I get a negative here. 2 minus 1 there is a positive, and so it looks like my curvature has changed to this shape. And then finally, if x is greater than 3, then everything is positive again. So I'm back to this shape. So by filling out this strip, we now have all the information we need to plot this chart. So let's see what it looks like. So let's mark our critical points. We've got a 0, obviously. We've got 1, and we've got 3 over here. Now we know the function itself has a double 0 at 0. The slope is going from negative to positive, and we said it was a minimum. So we know we're coming down this way. When x equals 1, we have a change in the second derivative curvature, and that means we're going from curving upwards to curving downwards. So this is our inflection point right here. And then when we get to 3, our slope is positive and then stays positive. So this is what our curve looks like. We've got a nice well-defined minimum, local minimum here. We've got a bona fide inflection point here, as shown by the change in curvature at that point. And we have another inflection point here as we're going from this kind of shape to this kind of shape. And that's how you do it. That's how we use the strip and the derivatives to help us build the curve. Let's see if we can make a simple flowchart to guide us through any problem that we have. Okay, so here's our flowchart. If we're given y is some function of x, and we're asked to plot that. First thing we do is we look for discontinuities. Things like vertical asymptotes and the behavior either side of the vertical asymptote. And similarly, horizontal asymptotes and the behavior on either side of that horizontal asymptote. Intercepts, and this is where we feed in x equals 0 for the y-axis and y equals 0 for the x-axis. So that's all the basic stuff that we've done before. The next thing we're going to do is calculate f dashed of x. And get the critical points. And that means f dashed of x equals 0 or does not exist. And we can also do f double dashed of x. And look for where f double dashed of x is 0 or does not exist. Once we have that, we make the strip table. And of course here we show critical points, and we can do the first derivative test for max and min, and we can do the second derivative test for inflection points. And then pretty much all we need is the end behavior of the function. What happens as x tends to plus or minus infinity, and finally we can graph it using all of that information gathered above. So that's kind of the set of logical steps to go through. The key new stuff is this derivative stuff, using the first and second derivative to help us find maxima, minima, inflection points, and other critical features of the function. And don't forget to like and subscribe if this has helped you in some way to understand this topic. Look forward to seeing you next time. Thanks very much. Enjoy the upcoming examples.